standard formula for calculating ohms per foot to determine voltage drop is based on Ohm's law. The fundamental voltage drop formula is voltage drop, measured in volts, equals current, measured in amps, times resistance, measured in ohms, times length, measured in feet. This is represented as voltage drop equals current times resistance times length. This formula determines the voltage loss over a specific length of conductor due to its inherent resistance. Now, if you need to determine the ohms per foot of a conductor, you can rearrange the formula. To solve for ohms per foot, you would divide the voltage drop by the product of the current and the length. This gives us ohms per foot equals voltage drop divided by, in parentheses, current times length. This rearranged formula allows us to calculate the resistance per unit length of the conductor if we know the acceptable voltage drop, the current flowing through it, and the length of the conductor. Let's delve deeper into each component of the formula. Voltage drop refers to the decrease in electrical potential along a conductor. It's the difference in voltage between the source and the load. Excessive voltage drop can lead to inefficient operation of electrical equipment, overheating, and even equipment failure. The National Electrical Code, or NEC, sets limits on the permissible voltage drop in branch circuits and feeders to ensure safe and efficient operation. Current is the flow of electrical charge through the conductor, measured in amps. The amount of current flowing through a conductor directly impacts the voltage drop. Higher current results in a greater voltage drop for a given resistance. Resistance is the opposition to the flow of current measured in ohms. The resistance of a conductor depends on its material, cross-sectional area, and temperature. Conductors with higher resistance will have a greater voltage drop for a given current. Length is the distance the current travels through the conductor, measured in feet. The longer the conductor, the greater the voltage drop for a given current and resistance. Now let's talk about how to apply these formulas in practice. Firstly, determine the acceptable voltage drop. The NEC recommends a maximum voltage drop of 3% for branch circuits and 5% for feeders. This provides guidelines for efficient system operation. Secondly, determine the current flowing through the conductor. This can be calculated based on the load connected to the circuit. Consider any future load additions when determining the current. Thirdly, determine the length of the conductor. This is the one-way distance from the source to the load. Accurately measure the conductor length to ensure accurate voltage drop calculations. Fourthly, use the rearranged formula to calculate the ohms per foot. Plug the values for voltage drop, current, and length into the formula to determine the required resistance per unit length. Fifthly, select a conductor with a resistance per foot less than or equal to the calculated value. Refer to conductor tables to find conductors with suitable resistance ratings. Ensure the selected conductor is also appropriately sized for the current it will carry, according to NEC ampacity tables. Consider the conductor material. Copper and aluminum are the most common conductor materials. Copper has lower resistance than aluminum for a given size, but it is also more expensive. Aluminum conductors are typically used for larger sizes to reduce costs, but require larger sizes than copper for the same ampacity and voltage drop performance. Consider the conductor temperature rating. Conductors are rated for specific operating temperatures. Ensure the selected conductor's temperature rating is suitable for the application and installation environment. Higher temperature ratings allow for higher ampacity, but may also require special terminations. Consider the installation method. The way a conductor is installed can affect its ampacity. Conductors installed in conduit or cable trays may have different ampacity ratings than conductors installed in free air. Refer to NEC tables for ampacity adjustment factors based on installation method. Consider ambient temperature. The ambient temperature surrounding a conductor can affect its ampacity. Higher ambient temperatures reduce the ampacity of a conductor. Refer to NEC tables for ampacity correction factors based on ambient temperature. Consider the number of conductors in a raceway or cable. When multiple current-carrying conductors are installed in a raceway or cable, their ampacity must be derated. This is because the heat generated by the conductors can raise the temperature within the raceway or cable. Refer to NEC tables for ampacity adjustment factors based on the number of conductors. When calculating voltage drop, it's important to use accurate values for all parameters. Small errors in current, length, or resistance can lead to significant errors in the calculated voltage drop. Use appropriate measuring instruments and consult reliable sources for conductor data. It's also important to consider the limitations of the voltage drop formula. The formula assumes a uniform current distribution and a constant conductor temperature. In some cases, these assumptions may not be valid, and more complex calculations may be required. For example, in non-AC circuits, inductive reactance can significantly affect voltage drop. In these cases, it may be necessary to use more sophisticated voltage drop calculators or software that take into account inductive reactance. When dealing with nonlinear loads, such as electronic equipment, the current waveform may not be sinusoidal. This can also affect voltage drop, and it may be necessary to use specialized equipment to measure the voltage drop accurately. The NEC provides guidelines for calculating voltage drop in these situations. Remember that voltage drop calculations are just one factor to consider when selecting conductors. It's also important to consider ampacity, insulation type, and environmental conditions. Consult the NEC and other applicable standards for complete conductor selection requirements. Proper conductor selection is essential for ensuring the safe and efficient operation of electrical systems. By following the guidelines outlined in the NEC and using accurate voltage drop calculations, you can minimize voltage drop, improve efficiency, and prevent equipment failures. In summary, to effectively calculate voltage drop and determine the appropriate conductor size, you need to understand the voltage drop formula and its components. Firstly, start with the basic voltage drop formula. Voltage drop equals current times resistance times length. Secondly, rearrange the formula to solve for ohms per foot, obtaining ohms per foot equals voltage drop divided by, in parentheses, current times length. Thirdly, determine the acceptable voltage drop based on NEC guidelines, typically 3% for branch circuits and 5% for feeders. Fourthly, determine the current flowing through the conductor, considering future load additions. Fifthly, accurately measure the length of the conductor from the source to the load. Sixthly, plug the values for voltage drop, current, and length into the rearrange formula to calculate the required ohms per foot. Seventhly, select a conductor with a resistance per foot less than or equal to the calculated value, referring to conductor tables. Eighthly, ensure the selected conductor is appropriately sized for the current it will carry, according to NEC ampacity tables. Ninthly, consider the conductor material, copper or aluminum, temperature rating, installation method, ambient temperature, and the number of conductors in a raceway or cable, applying appropriate adjustment and correction factors from the NEC. Tenthly, use accurate values for all parameters and be aware of the limitations of the voltage drop formula, especially in long AC circuits or with nonlinear loads. By following these steps and adhering to the NEC guidelines, you can ensure proper conductor selection, minimize voltage drop, and maintain the safety and efficiency of electrical systems. Always consult with a qualified electrical engineer or electrician for complex calculations or installations. The application of the voltage drop formula is crucial in electrical design and installation. Understanding the relationship between voltage drop, current, resistance, and length allows for the selection of appropriate conductors that meet both safety and performance requirements. Proper conductor sizing not only minimizes voltage drop but also ensures that the conductors can safely carry the intended current without overheating, preventing potential hazards. Furthermore, considering factors such as conductor material, temperature rating, and installation methods further enhances the reliability and efficiency of electrical systems. Regular inspections and maintenance of electrical systems can also help identify and address any issues related to voltage drop or conductor degradation, ensuring continued safe and efficient operation.